Bismillahirrahmanirrahim. Let's start the next lecture on heat and mass transfer. This lecture will start with the chapter number 1 problems from the book which is the Incorpora Indivit, and the problems which are numbered over here belong to the 7th edition of this book, the title of which is Fundamentals of Heat and Mass Transfer. Okay, we are going to start with 1-10. It says a freezer compartment. Over here is shown the freezer compartment consists of a cubical cavity which is 2 meters on a side, so it is a 2 by 2 by 2 meter cube. Assume the bottom to be perfectly insulated, so there would not be any heat transfer taking place from the bottom. So there would be 5 sides, top, and then left, right, and then front and back. So there would be 5 sides where the heat transfer will take from. What is the minimum thickness of the styrofoam insulation, K of which is 0.030 watts per meter Kelvin, that must be applied on the top and the side walls? So we need to find out the thickness, right? The thickness of the insulation means delta X, that must be applied to the top and the side walls, means 5 walls, to ensure a heat load of less than 500 watts. To ensure a heat load of less than 500 watts. So if the total heat transfer is to be less than or about 500 watts, then what should be the thickness? And because it is a freezer compartment, so heat will flow from the outside of this freezer to the inside, which will, of course, which needs to be reduced, which needs to be stopped. In order to accomplish this, the walls will be coated with some sort of insulation. So over here it is shown that the walls are insulated with the styrofoam insulation, right? And there are 5 such walls. So we need to find out its thickness. If the inner and outer surfaces are at -10 degrees Celsius and 35 degrees Celsius respectively, so inside the freezer the temperature is -10 degrees Celsius, whereas outside it is 35 degrees Celsius. So what we need to do is, first of all, my advice is that do not jump onto the values that are given. First of all, we should understand the problem. We should understand the modes of heat transfer that are taking place in any problem. See, we need to understand whether it is conduction which is taking place only, or whether it is convection which is taking place only, or radiation only, or it is a mixture of 2, or it is all 3. So we need to figure out which mode of heat transfer is taking place. For example, if we talk about this outer surface of this insulation, of course this insulation will not be facing the atmosphere, the surrounding, because what we see in a freezer is the outside sheet metal panel or plastic panel. So the insulation would be inside that panel, right? So over the outer surface of the refrigerator and the surrounding air, it would be convection and radiation as well, if the radiation is not negligible, right? So there would be convection and radiation. Whereas if we talk about the mode of heat transfer which is taking place through this insulation only, so across this insulation, through this insulation, it would be conduction, right? So the heat that will be transferred from the surrounding air to the sheet metal panel or to the outer surface of the refrigerator would be the same as the amount of heat that will be transferred from the from the from that sheet metal panel or from that plastic body to the insulation, and the same heat will flow through the insulation, and the same heat will then flow into the freezer or refrigerator if the system is under a steady state. If the system is working under steady state conditions, then the heat transfer through all the components will be the same. So over here, since we are given information regarding the styrofoam insulation, K of which is 0.030 watts per meter Kelvin. So what we will do is that we may consider the conduction through the insulation. Since we are not given the value of H, the value of convective heat transfer coefficient between the surrounding and the outside of this wall, we will not be focusing towards that side, towards convection between the body and the surrounding air, because we will only be focusing more towards that data which is provided to us and not to that data which has not been provided to us. So over here, since we are to find out the thickness of the insulation, so this is the thickness of insulation, right? This is the thickness of insulation, or this is the thickness of insulation, which is supposed to be the same on every side. So through this thickness of insulation, it would be conduction only. Through this thickness of insulation, it would be conduction only, and therefore we will start with applying the Fourier's law of heat conduction, which is K delta T over delta X minus K delta T over delta X. So heat will flow from higher temperature to lower temperature. So we can write the final temperature T2 minus the higher temperature T1, or we can then take this negative sign in here and then we can write it in this manner, and we can write it without the negative sign. So over here T1 minus T2 would mean T1 as higher temperature and T2 as the lower temperature. Otherwise over here it would mean lower temperature or final temperature minus the initial temperature. So it's a pretty simple problem. We are given that the heat transfer needs to be less than 500 watts, so we will take it as 500 watts. In this particular expression, Q is K and delta T over delta X. Kindly remember that Q is in watts, K is in watts per meter Kelvin or watts per meter degree Celsius. Both are the same things, because the temperature difference in degree Celsius is equal to the temperature difference in Kelvin. A is the area which is normal to the direction of heat flow. Delta T is the temperature difference between any two sections. Over here this would be the temperature difference at the two ends of the insulation. At the two ends of the insulation means this face or this wall of this face of the wall of insulation and this face of the wall of the insulation. And delta X would be the thickness. So Q is given to us as 500, K is given to us as 0.030. Area would be 2 by 2 meters on a one side, and there are 5 such sides, there are 5 such faces. T1 is minus 10 and then minus 35, because one temperature is 35 and the other temperature is minus 10. So we will get the thickness of the insulation as 54 millimeters. Kindly note that over here I should have written 35 first and then minus 10 over here. So 35 would be written over here and minus 10 would be written over here. because of the reason that I just explained, that if we are writing it in this form without a negative sign, so therefore T1 should be the higher temperature and T2 would be the lower temperature. So therefore it would be 35 minus 10, and we will get the answer as 54 millimeters. Okay, now let's take the next one, which is 115. Again, a reminder that those numbers are from the 7th edition of the book. It says the 5 millimeter thick bottom of a 200 millimeter diameter pan. So we have a pan over here, right? And then we have its bottom, the thickness of which is 5 millimeters. So this thickness is 5 millimeters. It may be made from aluminum, K of which is 240, or copper, K of which is 390. So we are also learning that copper is more conductive as compared to aluminum. Again, those conductivities are not constant quantities, rather they vary with temperatures, as discussed in one of the previous lectures. However, at a particular temperature that they have considered, we are given the conductivities of aluminum as 240 and that of copper as 390. By the way, the very first table in our book lists the conductivities of various materials. It lists the conductivities of solids, including metals and non-metals, and then some liquids, and then some gases. So you can refer to that table as well, just to have a look at it. Okay. Now it says that when used to boil water, the surface of the bottom exposed to the water is nominally at 110 degrees Celsius. So this surface which is exposed to the water, the upper surface of the which is exposed to the water, is at 110 degrees Celsius, right? And if the heat is transferred from the stove to the pan at a rate of 600, so this has been placed on a stove and the heat is being transferred from that stove into the pan. So this face of this pan will face the fire, right? So it will be at a higher temperature. If we call this as T1 and this as T2, so therefore T1 is at higher temperature, will be at higher temperature, and T2 will be at a lower temperature. So if the heat is transferred from the stove to the pan at a rate of 600 watts, so we are given Q as 600 watts, then what is the temperature of the surface in contact with the stove for each of the two materials? What is the temperature of the surface in contact with the stove? Means this surface which is facing the stove, which we are calling as T1. So we need to find out its temperature in case of both materials, in case of aluminum and copper. So again, when we consider this thickness of 5 millimeters, so again it is conduction. So when we would be considering the heat transfer through this bottom pan, it would be via conduction. So we would be applying the Fourier's law, which is minus K delta T over delta X, and we can then write it in this manner. Now over here we are given Q as 600 watts, K, if we work it out for aluminum first, is 240. Area, now area which is normal to the direction of heat flow, A is the area which is normal to the direction of heat flow. Since this is the direction of heat flow, right, this is the direction of heat flow, of course the circular pan, because it has a diameter of 200 millimeters, so the bottom is circular, so the circular pan is the area of that circular pan would be normal to the direction of this heat flow or heat flux. So it would be pi r square or pi by 4 d square, where diameter of this pan is given as 200. So we will put 200 millimeters or 0.2 meters over here, and then T1 is T1, that is the temperature that we have to find out, and T2 is 110 degrees Celsius. Kindly note that you may put the temperatures over here in degrees Celsius or Kelvin. So if we are putting T2 as 110 degrees Celsius, so we will get T1 in degrees Celsius as well. However, if we are putting it in Kelvin, so we would be getting T1 in Kelvin. Over delta x, the thickness of this pen. The thickness of this pen is in fact 5 millimeters, so this is 5 millimeters in the denominator. So we will get T1 as 110.4 degrees Celsius. So T2, which is 110, and T1 is only 110.4. So there is a very small difference. But mathematically that is correct, because T1 is greater than T2, but by a very small amount. See, this small difference is due to the fact that the material is highly conductive, right? Because we are using aluminum. It is a very conductive material, K of which is 240. So the material which is highly conductive will be less resistive. So it will not store heat, rather it will conduct heat quickly. It will diffuse the heat quickly. So therefore we can see that the temperature difference between the two phases, between T1 and T2, is very small. And the second thing which is the reason for such a small temperature difference is the thickness. The thickness is only 5 millimeters. Now if we increase the thickness from 5 to 10 or 15 millimeters, this temperature difference will increase. So the higher the thickness of the material, more would be the resistance and more would be the temperature difference between the two phases. Similarly, the lesser the conductivity of the material, means if the value of K is small, so the same phenomena will happen, means that it will offer more resistance, because if it is not highly conductive, then it is more resistive in nature. So it will not let the heat flow that easily. So it will also result in more temperature difference between the two phases. And if we work the same thing out for copper, we will get this temperature over here at the bottom surface as 110.24 degrees Celsius. Okay, let's take the next problem, which is 121. It says that an electrical resistance heater is embedded in a long cylinder. An electrical resistance heater is embedded in a long cylinder of diameter 30 millimeters. So we have got this cylinder, the diameter of which is 30 millimeters, and in it is an electric resistance heater. Now there may be various reasons for having such an arrangement, because probably there is an oil or something else that might be flowing inside it, or it may be simply water which is flowing inside it, and we just want to heat that water so as to supply the heated water. Or it may be a pipe carrying oil, and we might be heating up the oil so as to reduce its viscosity, and the reduction in viscosity will lead to lesser power requirements for pumping requirements. So there may be various reasons for which that electrical heater is embedded inside it. Now when water with a temperature of 25 degrees Celsius and a velocity of 1 meters per second flows crosswise over the cylinder, so if water flows crosswise in this direction over this cylinder at a temperature of 25 degrees Celsius, and a velocity of 1 meters per second, u infinity is 1 meters per second. So by now you would have realized that since water is flowing over the surface of the cylinder, so that would make it a case of convection, right? So if the water flows over this cylinder, the power per unit length required to maintain the surface at a uniform temperature of 90 degrees Celsius is 28 kilowatts per meter. The water if the water flows over this surface, the power per unit length required to maintain the surface at a uniform temperature of 90 degrees Celsius. So if the surface temperature, if the temperature of this surface is 90 degrees Celsius, then the power would be 28 kilowatts per meter. So we are given power per unit length, watts per meter. Now in the second case, they are changing the fluid. Now instead of water, they are considering air. When air also at the same temperature of 25 degrees Celsius, but with a velocity of 10 meters per second. So air is moving 10 times faster than water. Then what happens is that the power per unit length required to maintain the same surface temperature of 90 degrees Celsius is only 400 watts per unit length of the cylinder. So he is asking us to calculate and compare the convection coefficients for the two cases, for the case of water and air. So if you consider there would certainly be conduction in this case. See, the heater is inside, so inside the temperatures would be, inside the pipe the temperatures would be higher, right? And suppose that that there is some water or oil flowing, there is some fluid flowing through this pipe. So between the that fluid and the inner surface of the pipe, between the fluid and the inner surface of the pipe, it would be convection. It would be convection. The heat will then reach from the fluid to the inner surface of the pipe, and then the heat will then flow from the inner surface of the pipe to the outer surface of the pipe via conduction. See, when the heat will flow through the thickness of the pipe, it would be conduction only, and the heat will come out radially. Radially means it will flow in radial direction, because it is flowing from the inner surface, which is Ri, inner radius, to the outer surface, which is at R0, outer radius. So it will flow out, it will come out radially, in radial direction, and thus the heat will, or the energy will reach the outer surface. Sometimes over here many people, and I would also be using the heat and energy interchangeably, but you should keep in mind that energy can be stored and heat cannot be stored. It is the energy in transition, which was discussed in one of the previous lectures, probably in the very first lecture. So the heat will then reach to the outer surface, and from here water is flowing over the surface. So the heat will be convected away, will be taken away by the water, right? So between the outer surface and the water, there would be convection again. So there are at least two modes of heat transfer if we are not considering radiation for the time being. But since we have been asked to calculate and compare the convection coefficients for the two flows, so our focus will not be the convection between the inner fluid, which is inside the pipe, and the inner surface of the pipe, and our consideration will, our focus will not be over the heat transferred through the pipe thickness. See, we are not given the value of H inside the pipe, we are not given any information on the fluid which is flowing inside the pipe. See, we are not also given the inner and outer surface temperatures of the pipe, nor we are given the material of the pipe, right? So therefore we will be focusing on that, or rather we will start and focus on that portion where the information is provided about. So since we are asked to compare the convection coefficients of the two flows of the water and air over the cylinder, so our focus would be outside of the cylinder, and that is the data that has been provided to us as well. So we would start with HA delta T. Q is HA delta T, which is Newton's law of cooling, right? So now area through which the heat transfer is taking place is in fact this whole surface area of the pipe, which is 2 pi RL or pi dl. So we can write area as 2 pi RL or pi dl times Ts. Ts would be the temperature of the surface of the outer surface of the pipe, which is given to us as 90 degrees Celsius. T infinity is the temperature of the water in first case and the temperature of air in the second case, which is given to us as 25. Now since we are given the heat transfer per unit length, so what we can do is that we can bring this length on the right hand side, which is on the right hand side of the equation, onto the left hand side of the equation. So it would become Q by L, and we are given Q by L as 28 kilowatts per meter. We are given over here, it says the power per unit length is 28 kilowatts per meter. So we are not only being told, but because it says power per unit length, rather we are also if we look at the units, it says watts per meter, and watts per meter is Q by L. So Q by L is 28,000. H is the unknown. 2 pi R, where R is the radius. We are given that the diameter is 30, so 2 times R is 30. Ts is 90 and T infinity is 25. If we put the values, we will get H of air as 4570 watts per meter square Kelvin. Again, kindly note that H, convection coefficient, is not a material's property. However, K, which is the thermal conductivity, is a material's property. We have discussed it in detail in convection. Now for the second case, when the sorry, that was for air. So if we consider if we will start with the Newton's law of cooling, which is HA delta T, and if we start with water first, we can write H as H of water. Area would be the area through which this convection heat transfer is taking place, means this whole surface area, which is 2 pi RL or pi dl. So we can write this area as 2 pi RL or pi dl. Ts would be the temperature of the outer surface of the pipe, and T infinity would be the temperature of the water which is flowing over it. So water in the first case and then air in the second case. Now over here, if you see that we are given that Q in case of water is 28 kilowatts per meter, so it is the power per unit length. So area would be 2 pi RL. So if we bring this length into the denominator of Q, it would become Q by L, the value of which is 28 exponent 3 watts per meter. Kindly note that over here Q is in watts, H is in watt per meter square Kelvin, area is in square meter, and delta T is in Celsius or Kelvin. It does not matter, both would be the same. Now so we have put this Q by L as 28,000, and we are given that the diameter is 30, and the temperature of the outer surface of the cylinder is 90, and the water is flowing at a temperature of 25 degrees Celsius. So if we just put the values, we will get the value of H as 4570 watts per meter square Kelvin. Now if we work the things out for the case of air, now Q by L in case of air is 400 watts per meter. So we can put then 400 watts per meter over here, and then we will get the rest of the things would remain the same, and we will get H of air as 65. So H of water is 4570 and H of air is 65. Now you can see that H of water is greater than H of air. It means that when water is flowing over its surface, it will convect away more energy, a lot more energy. See, over here it is only 65, and on the other end it is 4570. The second thing is that the water was flowing at a velocity of 1 meter per second only, whereas the air was flowing with a velocity of 10 meters per second, 10 times faster. But even making the air flow 10 times faster will not make the edge of air fall anywhere near the edge of water. It is still only 65 and it is 4570. So this again leads to our discussion in the section of convection. It was probably the first or the second lecture, that the liquids will usually have a higher heat transfer coefficients, convective heat transfer coefficients, as compared to those of gases. Okay, let's take the next problem.